Welcome to this series of supply chain lectures. I'm Johannes Vermorel, and today I will be presenting forecasting lead times. Lead times, and more generally, all the applicable delays, are a fundamental aspect of supply chain. When attempting to balance supply and demand, one must consider the delays that are involved. For example, let's consider the demand for a toy. The proper anticipation of the seasonal peak of demand before Christmas doesn't matter if the goods are received in January. The lead times govern the fine print of planning just as much as demand does. Lead times vary. They vary a lot. This is a fact, and I will be presenting some evidence in a minute. However, at first glance, this proposition is puzzling. It is not clear why lead times should vary so much in the first place. We have manufacturing processes that can operate with less than a micrometer of tolerance. Furthermore, as part of the manufacturing process, we can control an effect, say the application of a source of light, down to 1 microsecond. If we can control the transformation of matter down to the micrometer and down to the microsecond with sufficient dedication, we should be able to control the flow of demands with a comparable degree of precision. Or maybe not. This line of thinking might explain why lead times appear to be so underappreciated in the supply chain literature. Supply chain books, and consequently supply chain software, barely acknowledge the existence of lead times beyond introducing them as an input parameter for their inventory model. For this lecture, there will be 3 goals. First, we want to understand the importance and the nature of lead times. Second, we want to understand how lead times can be forecast with a specific interest in probabilistic models that let us embrace the uncertainty. Third, we want to combine lead time forecast with demand forecast in ways that are of interest for supply chain purposes. According to the mainstream supply chain literature, lead times are barely worth a couple of footnotes. This statement might appear as an extravagant exaggeration, but I'm afraid it is not. According to Google Scholar, a specialized search engine dedicated to the scientific literature, the query demand forecasting for the year 2021 returns 10,500 papers. A cursory inspection of the results indicate that indeed the vast majority of those entries are discussing forecasting the demand in all sorts of situations and markets. The same query also for the year 2021 on Google Scholar for lead time forecasting returns 71 results. The results for the lead time forecasting query are so limited that it only takes a few minutes to survey an entire year worth of research. It turns out that there are only about a dozen entries that are truly discussing the forecast of lead times. Indeed, most matches are found in expressions like long lead time forecast or short lead time forecast that refer to a forecast of the demand and not to a forecast of lead time. It is possible to repeat this exercise with demand prediction and lead time prediction and other similar expressions and other years. Those variations yield similar results. I will be leaving that as an exercise to the audience. Thus, as a rough estimate, we have about 1,000 times more paper about forecasting demand than there are about forecasting lead time. Supply chain books and supply chain software follow suit, leaving lead time as a second-class citizen and as an inconsequential technicality. However, the supply chain personnel that have been introduced in this series of lectures tell a different story. Those personnel might be fictitious companies, but they reflect supply chain archetypes. Those personnel tell us about the sort of situation that should be considered as typical. Let's see what those personnel tell us as far lead times are concerned. Paris is a fictitious fashion brand operating its own retail network. Paris orders from overseas suppliers. Lead times are long and sometimes higher than 6 months. Those lead times are only imperfectly known, and yet the new collection must hit the store at the right time as defined by the marketing operation associated with the new collection. The supplier's lead time require proper anticipation. In other words, they require a forecast. Amsterdam is a fictitious FMCG company that specializes in the productions of cheeses, creams, and butter. The ripening process of cheese is known and controlled, but it varies with deviations of a few days. Yet, a few days is precisely the duration of the intense promotions triggered by the retail chains that happen to be the primary sales channel of Amsterdam. Those manufacturing lead time require a forecast. Miami is a fictitious aviation MRO. MRO stands for maintenance, repair, and overhaul. Every jetliner needs thousands of parts on a yearly basis to keep flying. A single missing part is likely to ground the aircraft. The repair duration for a repairable part, also referred to as the TAT, the turnaround time, defines when the rotable part becomes serviceable again. Yet the TAT varies from days to months depending on the extent of the repairs, which aren't known at the time the part is removed from the aircraft. Those TAT require a forecast. San Jose is a fictitious e-commerce that distributes a variety of home furnishing and accessories. As part of this service, San Jose provides a commitment for a delivery date for every transaction. However, the delivery itself depends on third-party companies that are far from being perfectly reliable. Thus, San Jose requires an educated guess about the delivery date that can be promised for every transaction. This educated guess is implicitly a lead time forecast. And finally, Stuttgart is a fictitious automotive aftermarket company. It operates branches delivering car repairs. The lowest purchase price for the car parts can be obtained from wholesalers that offer long and somewhat irregular lead times. Thus, there are more reliable suppliers that are more expensive and closer. Choosing the right supplier for every part requires a proper comparative analysis of the respective lead times assorted to the various suppliers. As we can see, through those, every single supply chain personnel presented so far requires the anticipation of at least one and frequently several lead times. While it could be argued that forecasting lead times require more attention and more effort than forecasting demand, it could be argued that forecasting demand requires more attention than forecasting lead time. In the end, both are needed for nearly all supply chain situations. Thus, let's have a look at a few actual real-world lead times. On the screen, there are 3 histograms that have been plotted by compiling observation of observing lead times associated to 3 mechanical parts. Those parts are ordered from the same supplier located in Western Europe. Those orders come from a company also located in Western Europe. The x-axis indicates the duration expressed of the observed lead times expressed in days. The y-axis indicates the number of observations expressed as a percentage. In the following, all the histograms will adopt the same conventions, with the x-axis associated with two durations expressed in days, and the y-axis reflecting the frequency. From those three distributions, we can already make a few observations. First, the data is sparse. We only have a tiny few dozen data points. Furthermore, those observations have been collected over several years. This situation is typical. If the company orders only once a month, then it takes almost a decade to collect over 100 observations of lead times. Thus, whatever we do in terms of statistics, it should be geared toward small numbers rather than large numbers. Indeed, we will rarely get the luxury of dealing with large numbers. Second, the lead times are erratic. We have observations ranging from a few days to a quarter, while it is always possible to compute an average lead time, relying on any kind of average value for any of those parts would be unwise. It is also clear that none of those distributions is even remotely normal, as in normal distributions. Third, we have three parts that are somewhat comparable in size and price, and yet lead times vary a lot. While it might be tempting to lump together those observations to make the data less sparse, it is obviously unwise to do so, as it would be mixing distributions that are highly dissimilar. Those distributions don't have the same mean, don't have the same median, or even the same minimum or maximum. Let's have a look at a second batch of lead times. Those durations reflect the time it takes to repair three distinct aircraft parts. The first distribution appears to have, on the top, appears to have two modes plus a tail. When a distribution presents two modes, it usually hints for the existence of a hidden covariable that explains those two modes. For example, there might be two distinct types of repairs operation, each type being associated with a lead time of its own. The second distribution appears to have one mode plus a tail. This mode matches a relatively short duration, about 2 weeks. It might reflect a process where the part gets inspected first, and sometimes the part is deemed serviceable without any further intervention, hence a much shorter lead time. The third distribution appears to be fairly spread, without an obvious mode nor an obvious tail. There might be multiple repair processes at play here that get lumped together. The sparsity of the data, we have only 3 dozen observations, make it difficult to say more. We will be revisiting this third distribution later in this lecture. Finally, let's have a look at two lead times reflecting the shipping delays from Taiwan to the West Coast, to the US West Coast, either by air or by sea. Unsurprisingly, cargo aircraft are faster than cargo ships. Also, the second distribution seems to hint that sometimes a sea shipment might miss its original ship and then get shipped with the next ship, almost doubling the delay. The very same phenomenon might be at play with the air shipment on top, although the data is so limited that it's only a wild guess. Let's point out that having access to only a couple of observations isn't out of the ordinary as far as lead times is concerned. Those situations are frequent. It is important to keep this in mind in this lecture, that we are seeking tools, instruments that let us work with the data, the lead time data we have, down to a handful observations, not the lead time data we wish to have, like thousands of observations. The short gaps in both distributions also suggest day-of-week cyclical pattern at work, although the present histogram visualization is not appropriate to validate this hypothesis. From this short review of real-world lead times, we can already grasp some of the underlying phenomena that are at play. Indeed, lead times are highly structured. Delays do not happen without cause, and those causes can be identified, decomposed, and quantified. However, the fine print of the lead time decomposition is frequently not recorded in the IT systems, at least not yet. However, even when an extensive decomposition of the observed lead time is available, as it might be the case in certain industries like aviation, it does not imply that lead times can be perfectly anticipated. Subsegments, phases within the lead time are likely to exhibit their own irreducible uncertainty. This series of supply chain lectures present my views and insights both on the study and on the practice of supply chain. I'm trying to keep those lectures somewhat independent, but those lectures make more sense when being watched in sequence. The rest of the present lectures depends on elements that I've previously introduced in this chapter, although I will be providing a refresher in a minute. The first chapter is a general introduction to the field and study of supply chain. It clarifies the perspective that goes into this whole series of lectures. As you might have surmised already, this perspective diverges substantially from what would be considered as the mainstream perspective on supply chain. The second chapter introduces a series of methodologies. Indeed, supply chain defeats naive methodologies. Supply chains are made up of people who have agendas of their own. There is no such thing as a neutral party in supply chain. This chapter addresses those complications, including my own conflict of interest as a CEO of Lokad, an enterprise software company that specializes in predictive supply chain optimization. The third chapter surveys a series of supply chain personae. Those personae are fictitious companies that we have reviewed briefly today, and they are intended to represent archetype of supply chain situations. The purpose of those personae is to focus exclusively on the problems, postponing the presentation of solutions. The fourth chapter reviews the auxiliary sciences of supply chain. Those sciences are not about supply chain per se, or rather they should be considered as essential for a modern practice of supply chain. This chapter includes a progression through the abstraction layers, starting from the computing hardware up to cybersecurity concerns. The fifth and present chapter is dedicated to predictive modeling. Predictive modeling is a more general perspective than forecasting. It's not just about forecasting the demand. It's about the design of models that can be used to estimate, to quantify future factors of the supply chain of interest. Today, we delve into lead times, but more generally in supply chain, anything that isn't known with a reasonable degree of certainty deserves a forecast. The sixth chapter explains how optimized decision can be computed while leveraging predictive models, and more specifically, probabilistic models that were introduced in the fifth chapter. The seventh chapter goes back to a largely non-technical perspective in order to discuss the actual corporate execution of a quantitative supply chain initiative. Today, we focus on lead times. We have just seen why lead times matter, and we have just reviewed a short series of real-world lead times. Thus, we will proceed with elements of lead time modeling. As I will be adopting a probabilistic perspective, I will be briefly reintroducing the continuous rank probability score, or CPRS, a metric to assess the goodness of a probabilistic forecast. I will also be introducing cross-validation and a minor variant of cross-validation that is suitable for our probabilistic perspective. With those tools in hand, we will introduce and assess our first non-naive probabilistic model for lead times. Lead times data are sparse, and the first item in our agenda is to smooth those distributions. Lead times can be decomposed into a series of intermediate phases. Thus, assuming that though some decomposed lead times data are available, we need something to recompose those lead times while preserving the probabilistic angle. Then we will be reintroducing differentiable programming. Differentiable programming has already been used in this series of lectures to forecast demand, but it can be used to forecast lead times as well. We will do so starting with a simple example intended to capture the impact of the Chinese New Year on lead time, a typical pattern observed when importing goods from Asia. We will then proceed with a parametric probabilistic model for lead times, leveraging the log-logistic distribution. Again, differentiable programming will be instrumental to learn the parameters of the model. We will then extend this model by considering incomplete lead time observation. Indeed, even purchase orders that are not completed yet give us some information about the lead time. Finally, we bring together a probabilistic lead time forecast and a probabilistic demand forecast within a single inventory replenishment situation. This will be the opportunity to demonstrate why modularity is an essential concern when it comes to predictive modeling, more important even than the fine print of the model themselves. In the lecture 5.2 about probabilistic forecasting, we have already introduced some tools to assess the quality of a probabilistic forecast. Indeed, the usual accuracy metrics like mean square error or mean absolute error only apply to point forecast, not probabilistic forecast. Yet, it's not because our forecast becomes probabilistic that accuracy in the general sense becomes irrelevant. We just need a statistical instrument that happens to be compatible with the probabilistic perspective. Among those instruments, there is a CPRS, or continuous rank probability score. The formula is given on the screen. The CPRS is a generalization of the L1 metric, that is, of the absolute error, but for probability distributions. The usual flavor of the CPRS compares a distribution named F here with an observation named X here. The value obtained from the CPRS function is homogeneous with the observation. For example, if X is a lead time expressed in days, then the CPRS value is also expressed in days. The CPRS can be generalized for the comparison of two distributions. This is what is being done on the screen. It's just a minor variation of the previous formula. The essence of this metric remains unchanged. If F is the true lead time distribution, and if F hat is an estimate of the lead time distribution, then the CPRS is expressed in days. The CPRS reflects the amount of difference between the two distributions. The CPRS can also be interpreted as the minimum amount of energy it takes to transport all the mass from the first distribution so that it takes the exact shape of the second distribution. We now have an instrument to compare two one-dimensional probability distributions. This will become of interest in a minute as we introduce our first probabilistic model for the lead times. Having a metric to measure the goodness of a probabilistic forecast isn't quite sufficient. the metric measures the goodness on the data we have. However, what we truly want is to be able to assess the goodness of our forecast on the data that we don't have. Indeed, it's the future lead time that are of interest to us, not the lead times that have been already observed in the past. Our capacity to model the capacity for a model to perform well on the data that we don't have is called generalization. Cross-validation is a general model validation techniques precisely intended to assess the capacity of the model to generalize well. In its simplest form, cross-validation consists of partitioning the observation in a small number of subsets. For each iteration, one subset is put aside and referred to as the test subset. The model is then generated or trained based on the other data subsets, referred to as the training subsets. After training, the model is validated against the test subset. This process is repeated a certain number of times and then the average goodness obtained over all the iterations represent the final cross-validated result. Cross-validation is rarely used in the context of time series forecasting due to the time dependence between observations. Indeed, cross-validation, as just presented, assume that the observations are independent. When time series are involved, backtesting is used instead. Backtesting can be seen as a form of cross-validation that takes time dependence into account. The cross-validation comes with numerous variants. The cross-validation techniques comes with numerous variants that reflect a vast array of potential angles that may need to be addressed. I will not be surveying those variants. For the purpose of this lecture, I will be using a specific variant where at every split, the training subset and the test subset have roughly the same size. This variant is introduced to deal with the validation of a probabilistic model, as we will see with some code in a minute. Let's revisit one of the real-world lead time that we have previously seen. On the screen, on the left, the histogram associated to the third aviation repair time distributions. Those are the same observation as seen previously. The histogram has merely been stretched vertically. By doing so, the two histograms on the left and on the right share the same scale. For this left histogram, we have about 30 observations. It's not much, but it's already more than what we will frequently get. The histogram on the left is being referred to as an empirical distribution. It's literally the raw histogram as obtained from the observations. The histogram has one bucket for every duration expressed in an integral number of days. For every bucket, we count the number of observed lead time. Due to sparsity, the empirical distribution looks like a barcode. There is a problem here. If we have two observed lead times at exactly 50 days, does it make sense to say that the probability of observing either 49 days or 51 days is exactly 0? It does not. Clearly, there is a whole spectrum of durations going on. We merely happen not to have enough data points to observe the real underlying distribution, which is most likely much smoother than this barcode-like distribution. Thus, when it comes to mind that it would be desirable to smooth this distribution. However, there is an indefinite number of ways of performing this smoothing operation. There might be smoothing methods that looks good, but that are not statistically sound. As a good starting point, we would like to ensure that a smooth model is more accurate than an the empirical one. It turned out that we have already introduced two instruments, the CPRS and the cross-validation, that will let us do that in a minute. The results are on display. The CPRS error associated to the barcode distribution is 1.6 days, while the CPRS error associated with the smooth distribution is 1.4. Those two figures have been obtained through cross-validation. The lower arrow indicate that in the sense of the CPRS, the distribution on the right is the most accurate one of the two. The difference between of 0.2 between 1.4 and 1.6 is not that much. However, the key property here is that we have a smooth distribution that doesn't erratically leave certain intermediate duration with a zero probability. This is reasonable as our understanding of the repairs tells us that those duration would most likely end up happening if repairs are repeated. The CPRS doesn't reflect the true depth of the improvement that we have just brought by smoothing the distribution. However, at the very least, lowering the CPRS confirms that this transformation is reasonable from a statistical perspective. Let's now have a look at the source code that has produced those two models and put those two histograms on display. All in all, this is achieved in 12 lines of code if we exclude the blank lines. As usual in this series of lectures, the code is written in Envision, the domain-specific programming language of Lokad dedicated to the predictive optimization of supply chains. However, there is no magic. This logic could have been written in Python, but for the sort of problems that we are considering in this lecture, Envision is more concise and more self-contained. Let's review those 12 lines of code. At line 1 and 2, we are reading an Excel spreadsheet that has a single column of data. This spreadsheet contains 30 observations. This data is gathered within a table named H, and that has a single column named days. At line 4, we are building an empirical distribution. The variable R has the data type renvar, and on the right side of the assignment, the renvar function is an aggregator that takes observations as inputs and return the histogram represented with a renvar data type as a result. The renvar data type is dedicated to unidimensional integer distributions. We did introduce the renvar data type in a previous lecture of this chapter. This data type guarantees constant memory, a constant memory footprint, and a constant for every histogram, and a constant compute time for each operation. The downside of the renvar as a data type is that a lossy compression is involved, although the data loss caused by the compression has been engineered to be inconsequential for supply chain purposes. At line 5, we are smoothing the distribution with the built-in function named smooth. Under the hood, this function replaces the original distribution with a mixture of Poisson distribution. Each bucket of the histogram is transformed into a Poisson distribution with a mean equal to the integer position of the bucket. And finally, the mixture assigns a weight to each Poisson distribution proportional to the weight of the bucket itself. Another way to understand what this smooth function is doing is to consider that it's equivalent to replacing every single observation by a Poisson distribution with a mean equal to the observation itself. All those Poisson distributions, one per observation, are then mixed. Mixing means averaging out the respective histogram bucket values. The renvars R and S won't be used again before the line 14, and 15, where they get displayed. At line 7, we start a Monte Carlo block. This block is a sort of loop. This block is going to be executed 100 times as specified by the 100 values that appears right after the Monte Carlo keyword. The Monte Carlo block is intended to collect independent observations that are generated according to a process that involves a degree of randomness. You might be wondering why there is a specific Monte Carlo construct in Envision instead of just actually having a loop, as it is usually the case with mainstream programming languages. It turned out that having a dedicated construct yields substantial benefits. First, it guarantees that the iterations are truly independent down to the seeds used to derive the pseudo-randomness. Second, it offers an explicit target for the automated distribution of the workload across several CPU cores or even across several machines. At line 8, we create a random vector of Boolean values within the table H. With this line, we are creating independent random values called deviates, true or false, for every line of the table H. As usual with Envision, the loops are abstracted away through array programming. With those Boolean values, we are partitioning the table H into two groups. This random split is used for the cross-validation process. At line 9 and 10, we are creating two ranvars named A and B respectively. We are using, again, the ranvar aggregator, but this time we are applying a filter with the when keyword just after the aggregator, the call to the aggregator. The ranvar A is generated using only the lines where the value in A is true. For B, it's the opposite. The ranvar B is generated only for using the lines where the value in A is false. At line 11 and 12, we collect the figures of interest from the Monte Carlo block. In Envision, the keyword sample can only be placed within a Monte Carlo block. It is used to collect the observations that are made while iterating many times through the Monte Carlo process. At line 11, we are computing the average error expressed in CPRS terms between two empirical distributions subsample from the original set of lead times. The sample keyword specifies that the values that are collected over the Monte Carlo iterations, the AVG aggregator, which stands for average, on the right side of the assignment, is used to produce a single estimate at the end of the block. At line 12, we do something that is almost identical to what happened at line 11. This time, however, we apply the smooth function to the ranvar B. We want to assess how close the smooth variant is from the naive empirical distribution. It turned out that it's closer, at least in CPRS terms, than its original empirical counterpart. At line 15 and 14 and 15, we put the histograms and the CPRS values on displays. Those lines generate the figures that we have seen in the previous slide. This script gives us our baseline for the quality of the empirical distribution of our model. Indeed, while this model, the barcode one, is arguably naive, it is a model nonetheless, and a probabilistic one at that. Thus, this script gives us also a better model, at least in the sense of the CPRS, through a smooth variant of the original empirical distribution. Right now, depending on your familiarity with programming languages, it may seem like a lot to digest. However, I would like to point out how straightforward it is to produce a reasonable probability distribution even when we don't have more than a few observations. while we have 12 lines of code, only the lines 4 and 5 represent the true modeling part of the exercise. If we were only interested in the smooth variant, then the renvar S could be written with a single line of code. Thus, it's literally a one-liner in terms of code. First, apply a renvar aggregation, and second, apply a smooth operator, and we are done. The rest is just instrumentation is in display. With the proper tools, probabilistic modeling, may it be lead time or something else, can be made extremely straightforward. There is no grand mathematics involved, no grand algorithm, no any grand software pieces. It is simple and remarkably so. How do you get a shipment 6 months late? The answer is obvious: 1 day at a time. More seriously, lead times can usually be decomposed into a series of delays. For example, a supplier lead time can be decomposed into a waiting delay as the order is put into a backlog queue, followed by a manufacturing delay as goods get produced, and finally followed by a transit delay as the goods get shipped. Thus, lead times can be decomposed. Thus, if lead times can be decomposed, it is also of interest to be able to recompose them. If we were to live in a highly deterministic world where the future could be precisely anticipated, then recomposing the lead times would be just a matter of plain addition. Going back to the example that I just mentioned, composing the ordering lead time would be the sum of the queuing delay in days plus the manufacturing delay in days plus the transit delay in days. Yet, we do not live in a world where the future can be precisely anticipated. The real-world lead time distribution that were presented at the beginning of this lecture support this proposition. Lead times are erratic, and there is little reason to believe that this will fundamentally change in the coming decades. Thus, future lead times should be approached as random variables. Those random variables embrace and quantify the uncertainty instead of dismissing it. More specifically, this means that each component of the lead time should also be individually modeled as a random variable. Back again to our example, the ordering lead time is a random variable, and it is obtained as the sum of 3 random variables, respectively associated to the queuing delay, the manufacturing delay, and the transit delay. The formula on the formula for the sum of 2 independent one-dimensional integer-valued random variable is presented on the screen. This formula merely states that if we get a total duration of z days, and if we have k days for the first random variable x, and then we must have z minus k days for the second random variable y. This type of summation is known, generally speaking, in mathematics as convolutions. While it seems that there is an infinite number of terms in this convolution, in practice we only care about a finite number of terms. First, all the durations that have, all the negative durations that have a 0 probability. Indeed, negative delay would mean traveling back in time. Second, for large delays, probabilities become so small that for practical supply chain purposes, they can reliably be approximated as zeros. Let's put those convolutions into practice. Let's consider a transit time that can be decomposed into 2 phases: a shipping delay followed by a clearance delay at the customs. We want to model those 2 phases with 2 independent random variables and then recompose the transit time by adding those 2 random variables. On the screen, the histograms on the left are produced by the script on the right. At line 1, the shipping delay is modeled as a convolution of a Poisson distribution plus a constant. The Poisson function returns a renvar, the data type. Adding 3 has the effect of shifting the distribution to the right. The resulting renvar is assigned to the variable c. This renvar is put on display at line 3. It can be seen on the left as the topmost histogram. We recognize the shape of a Poisson distribution that has been shifted to the right by a few units, 3 units in this case. At line 2, the custom clearance is modeled as the mixture of a Dirac at 0 and of a Poisson at 5. The Dirac at 0 happens 80% of the time. That's what this 0.8 constant means. It reflects the situations where most of the times the goods are not even inspected by customs and go through without any notable delay. Alternatively, 20% of the time the goods are inspected at customs, and the delay is modeled as a Poisson distribution of mean 5. The resulting renvar is assigned to a variable named d. This renvar is put on display at line 4, and it can be seen on the left as the middle histogram. This asymmetrical aspect reflects that most of the time customs do not add any delay. Finally, at line 5, we compute c plus d. This addition is a convolution, as both c and d are renvars, not numbers. This is the second convolution in the script, as a convolution already took place at line 1. The resulting renvar is put on display. It is visible on the left as the third and lowest histogram. This third histogram is similar to the first one, except that the tail is spreading much further to the right. Once again, we see that with a tiny few lines of code, we can approach non-trivial real-world effects such as clearance delays at customs. However, 2 criticisms could be made about this example. First, it doesn't say where the constants come from. In practice, we want to learn those constants from the historical data. Second, while the Poisson distribution has the advantage of simplicity, it might not be a very realistic shape for lead time modeling, especially considering fat-tailed situation. Thus, we are going to address those 2 points in turns. In order to learn parameters from data, we are going to revisit a programming paradigm that we have already introduced in this series of lectures, namely differentiable programming. If you haven't watched the previous lecture of this chapter, well, this is a sin, but I forgive you, and I invite you to have a look at them after the end of the present lecture. Differentiable programming is introduced in greater detail. Differentiable programming is a combination of 2 techniques, namely stochastic gradient descent and automatic differentiation. The stochastic gradient descent is an optimization technique that nudges the parameters one observation at a time in the opposite direction of the gradients. The automatic differentiation is a compilation technique, as in the compiler of a programming language. Automatic differentiation computes the gradients for all the parameters that appear within a general program. Let's illustrate differentiable programming with a lead time problem. This will serve either as a refresher or as an introduction, depending on your prior familiarity with this paradigm. We want to model the impact of the Chinese New Year on lead times associated with imports from China. Indeed, as factories are closing for 2 or 3 weeks for the Chinese New Year, the lead times get longer. The Chinese New Year is cyclical. It happens every year. However, it is not strictly seasonal, at least not in the sense of the Gregorian calendar. At lines 1 to 6, we are introducing some mock purchase order data with 4 observations, with both an ordered date and an received date. In practice, this data would not be hard-coded, but we would load this historical data from the company systems. At lines 8 and 9, we compute whether this lead time overlaps with the Chinese New Year. The variable t.overlap_CNY is a Boolean vector. It indicates whether the observation is impacted by the Chinese New Year or not. At line 12, we introduce an autodiff block. The table T is used as the observation table, and there are 1,000 epochs. This means that each observation, so each line in the table T, is going to be visited 1,000 times. One step of the stochastic gradient descent corresponds to one execution of the logic within the autodiff block. At lines 13 and 14, 2 scalar parameters are declared. The autodiff block will learn those parameters. The parameter A reflects the baseline lead time without the Chinese New Year effect. The parameter B reflects the extra delay associated to the Chinese New Year. At line 15, we compute X, the lead time prediction of our model. This is a deterministic model, not a probabilistic one. X is a point lead time forecast. The right side on the assignment is straightforward. If the observation overlaps the Chinese New Year, then we return the baseline plus the New Year components. Otherwise, we only return the baseline. As the autodiff blocks picks only a single observation at a time, at line 15, the variable t.overlap_CNY refers to a scalar value and not to a vector. This value matches the one line picked as the observation line within the table T. The parameters the parameter A and B are wrapped into the exponential function exp. This is a small differentiable programming trick. Indeed, the algorithm that pilots the stochastic gradient descent tend to be relatively conservative when it comes to the incremental variations of the parameters. Thus, if we want to learn a positive parameter that may grow larger than, say, 10, then wrapping this parameter into an exponential process speeds up the convergence. At line 16, we return a mean square error between our prediction x and the observed duration expressed in days, t.days. Again, inside this autodiff block, t.days is a scalar value and not a vector, as the table T is the table used as the observation table. The return value is treated as the loss that gets minimized through the stochastic gradient descent. The automatic differentiation propagates the gradients from the loss backwards to the parameter E and B. Finally, at line 19, we display the two values that we have learned respectively for A and B, that is the baseline and the New Year component of our lead time. This concludes our reintroduction of differentiable programming as a versatile tool that learns statistical patterns from data. We'll be revisiting the autodiff blocks with more elaborate situations. However, let's point out once more that even if it may feel a little bit overwhelming, there is nothing really complicated going on here. Arguably, the most complicated piece of code in this script is the underlying implementation of the function Chinese year start, called at line 8, that happened to be part of this envision standard library. Within a few lines of code, we introduce a model with two parameters, and we learn those parameters. Once again, this simplicity is remarkable. Lead times are frequently fat-tailed. That is, when a lead time deviates, it may deviate by a lot. Thus, in order to model lead time, it is of interest to adopt distributions that can reproduce those fat-tailed behaviors. The mathematical literature presents an extensive bestiary of such distribution, and quite a few would suit our purpose. However, merely surveying the mathematical landscape would take us hours. Let's just point out that the Poisson distribution does not have a fat tail. Thus, today I will be picking the log-logistic distribution, which happen to be a fat tail distribution. The primary justification for this choice of distribution is that the Lokad teams are modeling lead times through log-logistic distributions for several clients. And it happens to be working well with a minimal number of complications. Let's keep in mind, however, that the log-logistic distribution is in no way a silver bullet, and there are numerous situations where the Lokad teams model lead times differently. On the screen, we have the probability density function of the log-logistic distribution. This is a parametric distribution that depends on two parameters, alpha and beta. The alpha parameter is the median of the distribution, and the beta parameter governs the shape of the distribution. On the right, a short series of shapes that can be obtained through various beta values. While this density formula may look intimidating, it is literally textbook materials, just like the formula to compute the volume of the sphere. You may try to decipher and memorize this formula, but it's not even necessary. You just need to know that an analytical formula exists. Once you know that the formula exists, finding it back online takes less than a minute. Our intent is to leverage the log-logistic distribution to learn a probabilistic lead time model. In order to do this, we are going to minimize the log likelihood. Indeed, in the previous lecture, within this fifth chapter, we have seen that there are several metrics that are appropriate for the probabilistic perspective. A little while ago, we revisited the CPRS, the continuous rank probability score. Here, we revisit the log likelihood, which adopts a Bayesian perspective. In a nutshell, given two parameters, the log-logistic distribution tells us the probability to observe each observation as found in the historical dataset. We want to learn the parameters that maximize this likelihood. The logarithm, hence the log likelihood rather than the plain likelihood, is introduced to avoid numerical underflows. Numerical underflows happens when we process very small numbers very close to zero. Those very small numbers don't play well with floating point representation as commonly found in modern computing hardware. Thus, in order to compute the log likelihood of the log-logistic distribution, we apply the logarithm to its probability density function. The analytical expression is given on the screen. This expression can be implemented, and this is exactly what is done in the 3 lines of code below. At line 1, the function L4 is introduced. L4 stands for log likelihood of log-logistics. Yes, that's a lot of L's and a lot of logs. This function takes 3 arguments, the 2 parameters alpha and beta plus x, the observation. This function returns the logarithm of the likelihood. The function L4 is decorated with the keyword autodiff. This keyword indicates that this function is intended to be differentiated through automatic differentiation. In other words, gradients can flow backward from the return value of this function back to its arguments, the parameters alpha and beta. Technically, the gradient flows backward through the observation x as well. However, As we will keep the observations immutable during the learning process, the gradients won't have any effect on the observations. At line 3, we get the literal transcription of the mathematical formula just above the script. Let's now put things together with a script that learns the parameters of a probabilistic lead time model based on the log-logistic distribution. At line 1 and 3, we generate our mock training dataset. Again, real-world settings, in real-world settings, we would be using historical data instead of generating mock data. At line 1, we create a renvar that represents the original distribution. For the sake of the exercise, we want to learn back those parameters, alpha and beta. The log-logistic function is part of the standard library of Envision, and it returns a renvar. At line 2, we create the table H. It contains 1,000 lines. At line 3, we draw 1,000 deviates that are randomly sampled from the original distribution R. This vector h.days represents the training dataset. At line 6, we have an autodiff block. This is where the learning takes place. At line 7 and 8, we declare two parameters, alpha and beta. And in order to avoid numerical problems like division by 0, bounds are applied to those parameters. Alpha must remain greater than 0.01 and beta must remain greater than 1.0. At line 9, we return the loss. That is the opposite of the log likelihood. Indeed, by convention, the autodiff blocks minimize the loss function, and thus we want, and here we want to maximize the likelihood, hence the minus sign. The function log likelihood.log-logistic is part of the standard library of Envision, but under the hood is just the function L4 that we have implemented in the previous slide. Thus, there is no magic at play here. It is the automated differentiation that makes all the gradient flow backward from the loss to the parameters alpha and beta. At lines 11 and 12, the original distribution and the learn distribution are plotted. The histograms are capped at 200. This cap makes the histogram a little bit more readable. We will get back to that in a minute. In case you would be wondering about the performance of the autodiff portion of this script, takes under 80 milliseconds to execute on a single CPU core. Differentiable programming isn't just versatile, it also makes good use of the computing resources as provided by modern computing hardware. On these screens, we have the two histograms produced by our script that we have just reviewed. On top, the original distribution with its two original parameters, alpha and beta, at 80 and 4, respectively. At the bottom, the learn distribution with two parameters, learn through differentiable programming. Those two spikes on the far right are associated with the tails that we have truncated as those tails extend quite far. By the way, while it is rare, it does happen for certain goods to be received more than 1 year after they were ordered. Not for every vertical, certainly not for dairy, but for mechanical parts or for electronics, it does happen occasionally. While the learning process isn't exact, we get results within 1% of the original parameter values. This demonstrates, at the very least, that this log likelihood maximization through differentiable programming does work. In practice, the log-logistic distribution may or may not be appropriate. It depends on the shape of the lead time distribution that you are facing. However, we can pretty much pick any alternative parametric distribution. All it takes is an analytical expression of the probability density function. There is a vast bestiary of such distributions. Once you have a textbook formula, a straightforward implementation through differentiable programming usually does the rest. Lead times are not just observed once the transaction is final. While the transaction is still in progress, you already know something. You already have an incomplete lead time observation. Let's consider that 100 days ago you placed an order. The goods haven't been received yet. However, you already know that the lead time is at least 100 days. This duration, 100 days, represents the lower bound for a lead time that has yet to be observed completely. Those incomplete lead times are frequently quite important. As I mentioned at the beginning of this lecture, lead times dataset are frequently sparse. It's not unusual to have a dataset that only includes half a dozen observations. In those situations, it is important to make the most of every observation, including the ones that are still in progress. Let's consider the following example. We have 5 orders in total. 3 orders have already been delivered with lead time values that were very close to 30 days. However, the last 2 orders have been pending for 40 days and 50 days respectively. According to the first 3 observations, the average lead time should be around 30 days. However, the last 2 orders that are still incomplete disproves this hypothesis. The 2 pending orders at 40 and 50 days hint for a lead time substantially longer. Thus, we should not discard the last 2 orders just because they are incomplete. We should leverage this information and update our belief toward longer lead times, maybe 60 days. Thus, let's revisit our probabilistic lead time model, but this time with taking incomplete observations into account. In other words, we want to deal with observations that are sometimes just a lower bound for the final lead time. In order to do that, we can use the cumulative distribution function, or CDF, of the log-logistic distribution. This formula is written on the screen. Again, this is textbook material. The CDF of the log-logistic distribution happens to benefit from a simple analytical expression. In the following, I will be referring to this technique as the conditional probability technique to deal with censored data. Based on this analytical expression of the CDF, we can revisit the log likelihood of the log-logistic distribution. The script on the screen provides a revised implementation of our previous L4 implementation. At line 1, we have pretty much the same function declaration. This function takes an extra 4th argument, a Boolean value named is incomplete, that indicates, as the name suggests, whether the observation is incomplete or not. At line 2 and 3, if the observation is complete, then we fall back to the previous situation with the regular log-logistic distribution. Thus, we call the log likelihood function that is part of the standard library. I could have repeated the code of the previous L4 implementation, but this version is more concise. At line 4 and 5, we express the log likelihood ultimately observing a lead time greater than the current incomplete observation x. This is achieved through the CDF, and more precisely, the logarithm of the CDF. We can now repeat our setup with a script that learns the parameters of the log-logistic distribution, but this time in presence of incomplete lead times. The script on the screen is almost identical to the previous one. At lines 1 to 3, we generate mock data. Those lines have not changed. Let's point out that h.n is an auto-generated vector that is implicitly created at line 2. This vector numbers the generated lines starting at line 1. The previous version of this script wasn't using this auto-generated vector, but presently the h.n vector does appear at the end of line 6. Lines 5 and 6 are indeed the important ones. Here we censor the lead times. It is as if we were making one lead time observation per day and truncating the observations that are too recent to be observed in full. This means, for example, that a 20-day lead time initiated 7 days ago appears as a 7-day incomplete lead time. By the end of line 6, we have generated a list of lead times where some of the recent observations, the one that would terminate beyond the present date, are incomplete. The rest of the script is unchanged, except for the line 12, where the h.isComplete vector is passed as the fourth argument of the log likelihood function. Thus, we are calling at line 12 the differentiable programming function that we just introduced a minute ago. Finally, on the screen, the two histograms as produced by this revised script. The parameters are still learned with high accuracy while we are now in presence of numerous incomplete lead times. In order to validate that dealing with incomplete lead times wasn't an unnecessary complication, I've re-executed the script, but this time with a modest variation, with the 3-argument overload of the log likelihood function, the one that we use initially and that assumes that all the observations are complete. For alpha and beta, we get the values displayed at the bottom of the screen. As expected, those values do not match at all the original values of alpha and beta. In this series of lectures, this is not the first time that a technique has been introduced to deal with censored data. In the second lecture of this chapter, the loss masking technique has been introduced to deal with stockouts. Indeed, we typically want to predict future demand, not future sales. Stockouts introduce a downward bias as we don't get to observe all the sales that would have happened if the stockout hadn't happened. The conditional probability technique can be used to deal with censored demand data, as it happens with stockouts. The conditional probability technique is a bit more complex than loss masking, so it should probably not be used if loss masking is enough. In the case of lead times, data sparsity is the primary motivation. We may have so little data that it may be critical to make the most of every single observation, even the incomplete ones. Indeed, the conditional probability technique is more powerful than loss masking in the sense that it does leverage incomplete observations instead of just discarding them. For example, if there is one unit in stock and if this one unit in stock gets sold, then hence hitting a stockout, the conditional probability technique still makes use of the information that the demand was greater than 1, or greater or equal than 1. Here we get a surprising benefit of probabilistic modeling. It gives us a graceful way to deal with censorship, an effect that occurs in numerous supply chain situations. Through conditional probability, we can eliminate entire classes of systematic biases. Lead time forecasts are typically intended to be combined with demand forecasts. Indeed, let's now consider a simple inventory replenishment situation as illustrated on the screen. We serve a single product as the stock can be replenished by reordering from a single supplier. We are seeking a forecast that would support our decision to reorder or not from this supplier. We can reorder now, and if we do so, the goods will arrive at the point of time noted as first arrival. Later, we will have another opportunity to reorder. This later opportunity happens at a point of time noted as next order. And in this case, the goods will arrive at the point of time noted as the second arrival. The period indicated as the window of responsibility is the period that matters as far as our reorder decision is concerned. Indeed, whatever reorder we decide won't arrive before the first lead time. Thus, we have already lost control on servicing the demand for anything that happens prior to the first arrival. Then, as we will get a later opportunity to reorder, servicing the demand after the second arrival isn't our responsibility anymore. It's the responsibility of the next reorder. Thus, reordering while intending to serve the demand beyond the second arrival can and should be postponed until the next reorder opportunity. In order to support the reorder decision, which can be not reordering anything, there are two factors that should be forecast. First, we should forecast the expected stock on hand at the time of the first arrival. Indeed, if by the time of the first arrival there is still plenty of stock left, then there is no reason to reorder now. Second, we should forecast the expected demand for the duration of the window of responsibility. In a real setup, we would also have to forecast the demand beyond the window of responsibility as well in order to assess the carrying cost of the goods that we are ordering now, as there might be leftovers that spill into later periods. However, for the sake of concision and timing, we are going to focus today on the expected stock and the expected demand as far as the window of responsibility is concerned. This script implements the window of responsibility factors or forecast that we just discussed. It takes as input a probabilistic lead time forecast and a probabilistic demand forecast. It returns two distributions of probabilities, namely the stock on hand on arrival and the eligible demand as scoped by the window of responsibility. At line 1 and 2 are the setup. The lines 1 and 2 are the setup of the timelines. It starts on January 1st and ends on March 1st. Again, in a production setup, this timeline would not be hard-coded. At line 4, a simplistic probabilistic demand model is introduced, a Poisson distribution repeated day by day for the entire duration of this timeline. The demand will be 1 unit per day on average. I'm using here a simplistic model for the demand for the sake of clarity. In a real setup, we would, for example, use an ESSM. ESSM stands for Innovation State Space Model. State space models are probabilistic models, and they have been introduced in the very first lecture of this chapter. At line 5, another simplistic probabilistic model is introduced. This second model is intended for the lead times. It's a Poisson distribution shifted of 7 days to the right. The shift is performed through a convolution. At line 6, we define the initial stock on hand. At line 7, we define the order cycle. This value is expressed in days, and it characterizes when the next reorder will take place. From line 9 to 16, we have a Monte Carlo block that represents the core of the logic of interest of the script. Earlier in this lecture, we have already introduced another Monte Carlo block to support our cross-validation logic. Here we are using this construct again, but for a different purpose. We want to compute two RANVALs reflecting respectively the stock on hand on arrival and the eligible demand. However, the algebra of random variables is not expressive enough to perform this calculation. Thus, we are using a Monte Carlo block instead. In the third lecture of this chapter, I pointed out that there is a duality between probabilistic forecasting and simulations. The Monte Carlo block illustrates this duality. We start with a probabilistic forecast, we turn it into a simulation, and finally we convert the results of the simulation back into another probabilistic forecast. Let's have a look at the fine print. At line 10, we generate one trajectory for the demand. At line 11, we generate the arrival date for the first order, assuming that we are ordering today. At line 12, we generate the arrival date for the second order, assuming that we are ordering again one order cycle from now. At line 13, we compute what remains as stock on hand at the first arrival date. It is the initial stock on hand minus the demand observed for the duration of the first lead time. The max 0 states that the stock can't go into the negatives. In other words, we assume that we don't take any backlog. This no backlog assumption could be modified. The backlog case is left as an exercise to this audience. As a hint, differentiable programming can be used to assess the percentage of the unserved demand that converts successfully into backlogs, depending on how many days there are before the renewed availability of the stock. Back to the script. At line 14, we compute the eligible demand, that is the demand that happens during the window of responsibility. At line 15 and 16, we collect the two RANVALs of interest through the sample keyword. Unlike the first envisioned script of this lecture, this one, the one that was dealing with cross-validation, we seek here to collect distributions of probabilities from these Monte Carlo blocks, not just averages. On both lines, 15 and 16, the RANVAL that appears on the right side of the assignment is an aggregator. At line 15, we get a RANVAL for the stock on hand on arrival. At line 16, we get another RANVAL for the demand that happens within the window of responsibility. At line 18 and 19, those two RANVALs are put on display. And now let's pause for a second and reconsider this whole script. The lines 1 to 7 are merely dedicated to the setup of the mock data. The lines 18 and 19 are just displaying the results. The only actual logic happens over the 8 lines between line 9 and line 16. Debatably, all the actual logic is located, in essence, at line 13 and 14. With just a few lines of code, less than 10, no matter how we count, we combine a probabilistic lead time forecast with a probabilistic demand forecast in order to compose some sort of hybrid probabilistic forecast of actual supply chain significance. Let's note that there is nothing here that really depends on the specifics of either the lead time forecast or the demand forecast. Simple models have been used, but sophisticated ones could have been used instead. It would not have changed anything. The only requirement is to have two probabilistic models. so that it becomes possible to generate those trajectories. Finally, on the screen, the histograms as produced by the previous script. The top histogram represents the stock on hand on arrival. There is a 30% chance, roughly, to face an initial stock at 0. In other words, there is a 30% chance that a stockout may have happened by the last day just prior to the first arrival date. The average stock value might be something like 5 units. However, if we were to judge this situation by its average, we would be seriously misreading the situation. A probabilistic forecast is essential to properly reflect this, the initial stock situation, the stock on hand situation. The bottom histogram represents the demand associated with the window of responsibility. We have a 10% chance, roughly, of facing 0 demand. These results might also be perceived as surprising. Indeed, we started this exercise with a stationary Poisson demand of 1 unit per day on average, 1 unit per day. We have 7 days between orders. If it was not for the varying lead time, there should have been less than a 0.1% chance of getting a 0 demand over 7 days. However, the script proves that this occurrence is much more frequent. The reason is that a small window of responsibility may happen if the first lead time is longer than usual and if the second lead time is shorter than usual. Facing 0 demand over the window of responsibility means that the stock on hand is likely to become quite high at a point of time. Depending on the situation, this might or not be critical, but it might in, for example, if there is a stocking capacity limit or if the stock is perishable. Once again, the average demand, probably around 8, does not provide a reliable insight into what the demand looks like. Remember that we have obtained this highly asymmetrical distribution from an initial stationary demand, 1 unit per day on average. This is stationary. And we get something at the end that is very asymmetrical. This is the varying lead time effect in action. This simple setup demonstrates the importance of lead times when it comes to inventory replenishment situations. This situation demonstrates that from a lead time, from a supply chain perspective, isolating lead time forecast from the demand forecast is at best a practical abstraction. The daily demand is not what we are truly interested in. What is of true interest is the composition of the demand with the lead time. If other stochastic factors were present, like backlogs or returns, then those factors would have been part of the model as well. The present chapter in this series of lectures is titled Predictive Modeling instead of demand forecasting, as it would typically be the case in mainstream supply chain textbooks. The reason for this chapter title should have become progressively obvious as we progress through the present lecture. We, indeed, from a supply chain perspective, we want to forecast the evolution of the supply chain system. Demand is certainly an important factor, but it's not the only factor. Other varying factors, like lead time, must be forecast. Even more importantly, all those factors must be, in the end, forecast together. Indeed, we need to bring those predictive components, let's call them that, together to support a decision-making process. Thus, what matters is not seeking some sort of endgame demand forecasting model. This task is largely a fool's errand, because ultimately the extra accuracy will be gained in ways that run contrary to the best interest of the company. More sophistication means more opacity, more bugs, more computing resources. As a rule of thumb, the more sophisticated the model, the harder it becomes to successfully, operationally compose this model with another model. What matters is to assemble a collection of predictive techniques that can be composed at will. This is what modularity is about from a perspective of predictive modeling. In this lecture, half a dozen of techniques have been presented. Those techniques are useful as they address critical real-world angles like incomplete observations. Those techniques are simple as well. None of the code example presented today exceeded 10 lines of actual logic. Yet, most importantly, those techniques are modular. Like Lego bricks, they work well together and they can be almost endlessly recombined. The endgame of predictive modeling for supply chain, as it should be understood, is the identification of such techniques. Each technique should be, by itself, the opportunity to revisit any pre-existing predictive model in order to simplify or improve this model. In conclusion, despite lead time being largely ignored by the academic community, lead time can and should be forecast. By reviewing a short series of real-world lead time distributions, we have identified two challenges. First, lead time vary. Second, lead times are sparse. Thus, we have introduced modeling techniques that are appropriate to deal with lead times observation that happen to be both sparse and erratic. Those lead times models are probabilistic, and those models are, to a large extent, the continuation of the models that have been gradually introduced through this chapter. We have also seen that the probabilistic perspective does provide an elegant solution to the problem of incomplete observation, an almost ubiquitous aspect in supply chain. This aspect or problem happens whenever there are stockouts and whenever there are pending orders. Finally, we have seen how to compose a probabilistic lead time forecast with a probabilistic demand forecast in order to craft the predictive model that we need to support a later decision-making process. Excellent. The next lecture will be on the 8th of March. It will be a Wednesday at the same time of the day, 3 p.m. Time of Paris. Today's lecture was technical. But the next one will be largely non-technical. I will be discussing the case of the supply chain scientist. Indeed, mainstream supply chain textbooks approach supply chain as if forecasting models and optimization models emerge and operate out of thin air, entirely ignoring their wetware command, that is, the people in charge. Thus, we will have a closer look at the roles and responsibilities of the supply chain scientist, the person who is expected to spearhead the quantitative supply chain initiative. And now I will be proceeding with the questions. Okay, we have a first question from Harsh Entrepreneur. What if someone wants to keep their stock for further innovation or for reasons, for other reasons, rather than just in time or other concepts? This is indeed a very important question. Here, this concept is typically addressed through the economic modeling of the supply chain. So what we technically called in this series of lectures, the economic drivers. So literally the question that you're asking is that I prefer not to serve a customer today because at a later point of time, there will be an opportunity where I will be able to serve the same unit to another person that matters more for whatever reason. So in essence, what you're saying is that there is more value to be captured by serving another customer later, maybe a VIP customer, later than serving a customer today. This might be the case. It does happen. If I were to take, an aviation example, let's say you are an MRO provider, you have your usual VIP clients, the airlines that you are serving very routinely. Those are, you have like long-term contracts and they are very important. So when this happens, you want to make sure that you will always be able to serve those parts. But what if, another airline just happened to ask to give you a call and ask for one unit? In this case, what will happen is that you could serve this person, but you don't have a long-term contract with them. So what you're going to do is to adjust your price so that it's very, very high, so that you get enough value to make up for the potential stockout that you may face at a later point of time. So bottom line for this first question, I believe that it's not really a matter of forecasting, but more a matter of proper modeling of the economic drivers. And if you want to preserve stock, what you want is to generate a model, an optimization model, where the rational response is to not serve the client that is asking one unit for you while you still have stock in reserve. By the way, another typical situation for that is when you're selling kits. A kit is like in order to, let's say you have a kit that is valued $1,000. It's made of many parts. That is your kit. And you have just one part left that is worth only, let's say, $20. The problem is that if you sell this last one unit at $20, then you can't build your kit and you can't sell your $1,000 kit anymore. And thus, you might be ending in a situation where you prefer to keep the unit in stock just for the sake of being able to sell at a later time, potentially with some uncertainty, the kit. But again, it boils down to the economic drivers. So that would be the way I would approach this situation. Now we have a second question from Xenia M, and I'm very sorry if I am botching the names. Please don't hate me for that. During the last few years, most of supply chain delays happened because of the war or pandemic, which is very difficult to forecast because we didn't have such situation before. What is your take on this? My take is that lead times have been varying forever. I mean, I've been in the supply chain world since 2008, and my parents were have been doing supply chain stuff, even almost 30 years before me. And as far we can remember, the family can remember, lead times have been erratic and varying. So there is always something, it can be just look at history. There is always a protest, a war somewhere, tariffs that get changed by a president. There is always stuff that happens. So yes, the last couple of years have been exceedingly erratic, but this is just the variations between having a lead times that vary from 5 days to 100 days to a lead times that varies from 5 days to 200 days. Yes, it's more variation, but it was already varying quite a lot. So I do agree. So you see, the essence is nobody can pretend to be able to forecast the next war. I can't, I don't think that seriously, if you were to be able to do this sort of forecast, you would not do supply chain. You would just play the stock market and become rich, anticipating the move of the stock market. So I believe it is a safe assumption that nobody can, and that there is no such mathematical trick. Nobody can predict mathematically the outcome of a war. If it was possible, people would not engage in the said war. So the bottom line is that what you can do is plan for the unexpected. Again, I say you have a distribution that's spread. If you're not confident into the future, you can actually inflate the variations. That's an interesting take. It's the opposite of trying to make your forecast more accurate. You preserve, your average expectations, but you just inflate the tail, so that the decision that you take on top of those probabilistic forecasts are more resilient to variation, because you've engineered your expected variations to be, larger than what you're currently seeing. So the bottom line is, you see, the idea that there are things that are easy or difficult to forecast, this is very much the point forecast perspective, where you would like to play the game as if it was possible to have a precise anticipation of the future. This is not the case. There is no such thing as a precise anticipation of the future. The only thing that you can do, really, is to have those probability distribution with a large spread that manifest and quantify your ignorance of the future. And it's fine. It is better to have this, and that's the reason why in practice those probabilistic forecasts really shine, is that instead of fine-tuning decisions that are depending from, I would say, critically depending from the minute execution of the exact plan, you are you're planning for stuff that will have an intrinsic degree of variation, and suddenly your decisions are made quite robust against those variations. Again, I'm only talking about the sort of variation that don't literally, that don't impact your supply chain in ways that are too brutal. For example, you can deal with that for a longer supplier lead time, but if you happen to be, in Ukraine, in a site that have just been bombed, then, no forecast is going to save the fact that your warehouse has just burned. Now, the third question from Mukul Sharma, and apparently there is another question that is very similar from Gurut Gera. Can we create these histograms and calculate the CPRS in Microsoft Excel? For example, by using Excel add-ins like XLStat, which host many distributions. So here, the answer is yes, you can. Yes, you can. One of us at Lokad has actually produced an Excel spreadsheet that represents a probabilistic model for an inventory replenishment situation in Excel. The crux of the problem is that Excel does not have a random data type. So all that you have in Excel are numbers. One cell, one number. But you see, the magic, if you want to make it very elegant, very simple, is to be able to have one value that is an histogram, where you have like a full histogram packed in one cell. The problem is that it is not exactly possible in, as far as I know, in Excel. Nevertheless, if you're willing to actually spend, 100 lines or so to represent a histogram, so it will not be such a compact and super practical representation for the distribution, yes, you can actually implement a distribution in Excel, and you can do some probabilistic modeling. We will be posting the link, I think, in the comments section. But we have crafted a probabilistic model in Excel. Disclaimer, it is a relatively painful undertaking, just because Excel is not like super suitable, but because the fact that Excel is a programming language, you can do anything. So you don't actually even need an add-in to do that. You can just do that with plain Excel. But it is a little bit verbose. So don't expect something that is like super nice and tidy. Another question that comes from Khan. Lead time can be broken down into components: order time, production time, transportation time, etc. If one wants a more granular control over the lead times, how would this approach change? The question would be, first, what does that mean to have more control over the lead time? Do you want to reduce the lead time, on average, or do you want to reduce the variability of the lead time? The interesting thing is that I've seen many companies that succeed in reducing the average lead time, but by trading some extra lead time variation. So on average, the lead time is shorter, but once in a while, it's way longer. So you see, it's interesting because, again, there is no free lunch. So this approach, fundamentally, here in this lecture, what we are doing is a modeling exercise. That's what we did today. By itself, there is no action. It's just about, observing, analyzing, and predicting. We don't do anything. This is just this predictive modeling chapter. However, what it does is that if we can decompose the lead time and we can analyze the underlying distribution, we can through those probabilistic modeling assess first which are the components that are varying the most truly, and which are the ones that are truly in the end generating the biggest negative impact on our supply chain. So you see, it's interesting because here we have to engage into what-if scenarios. I've decomposed my lead times in many pieces, and now I take one of those pieces and I do a what-if. What if the tail of this lead time was a little bit shorter, or if the average was a little bit shorter, or if something else? And then you can actually do that specifically on this portion of your lead time, recompose everything, rerun your whole predictive model for your whole supply chain, and start assessing the impact. And that's where it gets very, very powerful, is that it lets you reason piecewise about certain phenomena, including the erratic ones. So that would be, how I would approach that. It would not be like so much a change of approach, but just a continuation of what we have done, down to what is actually treated in the chapter 6, which are the optimization of actual decision based on those probabilistic model. A question from Albert Galosa. I believe this offers the opportunity to recalculate our lead times in SAP to provide a more realistic time frame and help minimize our system pull in and pull out. Is it possible? That's a tough question. Disclaimer, SAP is a competitor of Lokad as far the supply chain optimization is concerned. So my vendor answer is no, it's not possible. SAP can't ever do that. The reality, the first answer is SAP is, as far as I know, because SAP has actually 4 distinct solutions, 4 different stacks that deals with supply chain optimization. So it depends on which stack you're actually talking about. But all those stacks are in common to have, as a cornerstone, to have a vision centered on point forecast. You see, so everything has been engineered in SAP on the premise that the forecasts are going to be accurate. This is an assumption that goes like super deep into everything, the entire technological stack. So yes, you can, and SAP has some parameters to tune, those normal distribution I was mentioning. At the very beginning of this lecture, I mentioned that the lead time distribution that we observed were absolutely not normally distributed. So to my knowledge, again, there is so many different SAP setups that I can't say that it's going to be true for all the SAP setups, but the mainstream SAP setups, the most popular, widely adopted SAP setups for supply chain optimization, like APO, adopt normal distributions for the lead times. So in a sense, the problem is that at the core, the software is making a widely incorrect mathematical assumption. So you can't recover from a widely incorrect assumption that goes right into the core of your software architecture by tuning a parameter. I mean, maybe you can do some crazy reverse engineering and figure out a parameter that would end up doing something that would end up into generating the right decision. That might be possible. I mean, literally, that would mean that you build a correct modelization that doesn't make crazy assumptions like normal distribution. You get the results that you want, and then you play SAP with various lead times values, and until you figure out the lead time values that gives you a result, a production or reordering results that match what the correct result is doing. I mean, theoretically, this is possible. In practice, this is so much a problem, so that should be the question of why do you really want to do that. And so you see, that's the problem, is that you can't really adopt this probabilistic perspective piecewise. If you say that you want to go for this probabilistic vision, you have to be all in. So that means that your forecasts are probabilistic and your optimization models are leveraging probabilistic models as well. The problem here that we're saying is that even if we could tune with probabilistic modeling slightly better lead times, the rest of the SAP stack is going to fall back into point forecasts. So no matter what happens, we are going to collapse those distributions into points. And remember the last example that I gave for this inventory situation, the stock on hand on arrival, that was just the final part of this lecture. This distribution cannot be reasonably approximated by average. This is the idea that you could do that is troubling. This is just wrong. So that's the problem, is that, yeah, technically you could tune lead times, but you're going to run into so many problems after that it might not be really worth the effort. Another question from Manuel Lopez. There are situations where you order the same parts from different suppliers. This is an important information to process the lead time forecasting. Do you do lead time forecasting by item, or there are situations where you take advantage of the two groups of items in families? Well, this is a remarkably interesting question. So we have two suppliers for the same item. So it's interesting. The question will be how much similarity there is between the items and between the suppliers. Here, I mean, at first level, we need just to look at the situation. If one supplier happened to be next street and the other supplier happened to be the other side of the world, you really need to consider those things as separate. But let's assume the interesting situation where the two suppliers are fairly similar, and this is same item, fairly similar. Should you actually lump together those observations or not? The interesting thing is that through differentiable programming, you can actually compose a model that would give some weight to the supplier and give some weight to the item, and let the learning magic do its magic and fit wherever we should actually put more weight on the item component of the lead time or on the supplier component. Because you see, we can have something that is interesting. It might be that two suppliers serving pretty much the same sort of products might have some sort of bias where one supplier is on average a little bit faster than the other, but there are items that definitively takes more time. And thus, if you cherry pick items, you will see that it's not very clear that one supplier is faster than the other, because it really depends on which items you're looking at. And again, you have most likely very little data if you disaggregate everything down to every supplier, every item. Thus, the interesting thing, and that's what I would recommend here, would be to engineer through differentiable programming. We might actually try to revisit this situation in a later lecture, a situation where you put some parameters at the part level and some parameters at the supplier level. So you have a number of parameters, total number of parameters that is not the number of parts times the number of suppliers. That would be the number of parts plus the number of suppliers, or maybe plus the number of supplier times categories or something. You see? So you don't explode your number of parameters. You just add a parameter, an element that is that has an affinity to the supplier, and that lets you do some kind of dynamic mix that is driven by your historical data. A question from Guilherme Kawamata. And that's on top of the previous question from Mr. Manuel Lopez. I believe the quantity that is ordered and also which products that are ordered together might also impact the lead time in the end. Could you go over the complexity of including other variables in this type of problem? Okay, so here we are lumping together things that are of completely different nature. In the last example, we had actually two types of duration. We had the order cycle, and in the last example, I said the order cycle is 7 days. You know, it's just an assumption that I'm making, period. And then we had the lead time itself, which is something erratic and varying. But the order cycle was not erratic and varying. It was literally assumed that I will be ordering potentially now and 7 days from now. So here, the two things that we are lumping together are the order cycle and the actual supplier lead time. The order cycle is interesting because it is only uncertain to the extent that we haven't taken the decision yet. But it is fundamentally, I can decide pretty much, if I have the budget, to reorder at any point of time. So the ordering cycle is something that is entirely internal. It is of your own making. And that's very interesting because it's not the only thing. For example, in supply chain, prices are the same. You have demand, you observe demand, but you can actually pick the price that you want. Some prices are obviously unwise, but it's the same thing. It is of your own making. So the order cycle is of your own making. Now, what you're saying is that there is an uncertainty about the exact point of time for the next order lead time because you don't know exactly when you will be ordering. And indeed, you're completely correct. What happens is that when you have the capacity to have this probabilistic modeling in place, suddenly, and that's something that is from the 6th chapter of this series of lecture, suddenly you don't want to say the order cycle is 7 days. You want to say, I want to adopt the reordering policy that maximizes the return on investment for my company. And thus, what you can do is actually play the future so that if you reorder now, you can take a decision now, and then you apply your policy day by day, and then at some point of time in the future, you do a reordering. And now what you have is a kind of snake eating its tail, because the best ordering decision for today depends on the decision of the next ordering decision, the one that you have not taken yet. So it's kind of slightly puzzling. This sort of problem is known as a policy problem, and it's about it's a sequential decision problem, and it is under the hood. What you really want is to craft some sort of policy. It's a mathematical object that governs your decision-making process. Now, the problem of policy optimization is quite complicated, and I intend to cover this into the 6th chapter. But the bottom line is that we have, if we circle back, I'm sorry for this long answer, circle back to your question, is that we have really two distinct components. We have the component that varies independently on whatever you do, of the lead time, that's your supplier lead time, and then you have the ordering lead time, which is something that is really internal, driven by your process, and that should be treated as a matter of optimization. And then we have, and that will be the concluding thought, is that we see a convergence of optimization and predictive modeling. In the end, the two end up pretty much into being the same thing, because there are retraction effects between the decision that you take and what happens in the future. Excellent. I guess this is it for today. So don't forget, the 8th of March, same time of the day. It will be a Wednesday, 3 p.m. time of Paris. See you next time.